Thanks everyone for joining. I'm super pumped to give this talk. Designing large-scale systems is a very big part of my job and every other engineer's job at Google, especially SREs, which I'll talk a little bit about. So today, talking about designing large-scale distributed systems. If you're currently at Codesmith or a student, then this is, some good system design prep for the interviews. For alumni, I hope that you can gain some principles to keep in mind in your current job or a future job, or maybe even think about like what SRE might mean for you. So at the very top of the slide is a link to a Q&A system. We had a lot of people RSVP, so it might be hard to do live questions. So feel free to throw them in there. And I'll try to check that periodically. I'm on call this week, so there's a very small chance that I'll get pulled in to go deal with an incident at work. I have someone else covering me, but I am now my backup's backup. So just an FYI, there's a very small chance I'll have to duck out. But fingers crossed that does not happen. I actually, when I gave a talk a couple weeks ago, I had caused an incident that triggered while I was giving the talk, and I found out about it when I left. Everything was fine, and we learned a ton, and I think that was a good example of a blameless culture at Google, where it's actually encouraged to break stuff, which I absolutely did. So we can get started. So a little bit about me and the team that I work on. So I joined Google in 2019 after being a part of the Codesmith LA 15 cohort in 2017. I'm currently working as a software engineer in site reliability engineering. So we are the people who make sure that Google stays running and reliable and meets the expectation that everyone has about Google's uptime. Specifically, I'm on Access SRE, which we talked a little bit about. So it's really about getting corporate access for Googlers. And though, it may not be the billions of users in Gmail or Photos or YouTube, we still have 100,000 plus global Googlers that are using our services all day, every day. So these are pretty beefy, big systems, and we definitely have to design for them to be distributed. So you want to design a large-scale distributed system like we do at Google. This talk is going to talk about some like high-level principles about the distributed system design, as well as a few like examples on how we can implement them. Large systems especially need to handle failure gracefully every minute of every single day, because as your size keeps scaling up, the chance that that one hard drive or that one network connection breaks just basically converges to 100% chance. It is constantly failing. So first, we're going to talk about some architectural principles. So we'll go over, a key part of any sort of design process, especially system design. Very good and very important in interview questions is requirements gathering. Then we're going to talk about, this is part of requirements gathering. We'll talk about identifying the limiting factors of the system, the ways that system could fail, and then some principles. So keeping it simple, talking about state and replication. So first, we need to define how large a system needs to be and what kind of shape that it takes. So that means like, how much time does it take to build, and what is the cost of downtime, more importantly? So in terms of revenue, if your system is down, how much money do you lose? Do you lose reputation? Like, is there going to be a news article if the system goes down? If something goes down, will it have a cascading effect of taking other things down, which themselves cost money? If you lose data, what does that cost? Same kind of questions. Then we can think about the systems themselves. Like what's the throughput? So like how many requests are we expecting to see? What kind of data is going to come in? Are we talking about a little request with just like some JSON, which might be really cheap? Or is it going to be these big blobs of data, big images or videos where each request can be really expensive? When we take all of these components, what we can do is we can define this thing called the service level objective, which is a quantifiable agreement for what availability we're promising for the service. Since 100% is never a reasonable availability target because things are always failing, we need to have some number that we're trying to hit. And that requires business, that requires the developers, that requires the people who maintain the system to all agree on that number. And with that, we can then design our system. I don't want to go too much into SLOs. It's an absolutely massive topic and the foundation of SRE. Super interesting. I'd recommend taking a look at that, but out of the scope of this talk. So as part of requirements gathering, let's identify the limiting factors of our system. So if we want our system to grow and grow because we are getting more and more users, we have more and more content, we want it to stay healthy. So that means we don't get paged at 2 a.m. when there's some spike in traffic as a bunch of users try to do something. There's a couple of main ideas that we have to explore to understand our limiting factors and our failure modes. So the limiting factors are what govern the growth the limiting factors are what govern the growth of the system. So these can be the design decisions that like make it hard for a system to grow. So you can imagine that if we are getting a bunch of image traffic, we're getting a bunch of image uploads, now we have to have a limiting factor of like how much storage can we maintain? How available is that storage? How much downtime can we have when we need to say replicate that or restore from a backup? So the other part is we need to consider our failure modes. So these allow us to build a service that is resilient against like the forces of darkness that may take our service down, which is a little more evil sounding when really we mean we have a bunch of users who want to do a bunch of cool things. So these are the actual issues that can cause the image to tip over and fail, where the before we're talking about like how can we successfully grow? Now we're talking about like what would actually tip over that big thing that has grown. And these can be, you know, internal things. These can be external sources. And the goal is to design our system such that the failure modes are prevented before they start. We want to be proactive rather than reactive. So that was all kind of like abstract thinking. What's more interesting is talking about the specific stuff. And before we get into the specifics, I want to define a couple of terms that are going to be used throughout. So first, machine, this is the physical hardware that is running an operating system. So I have a Chromebook that I'm like streaming from right now. That is the machine, is the Chromebook. The operating system, Linux, Chrome OS, is what's running on it. QPS, so this is a very common term, or queries per second. So how many requests, aka queries, a given service is handling per second. This is a measure of volume that we constantly use. The server, so this is an individual process or binary that's running on a machine. So this is like a single instance of Gmail running on a single server in a data center. The service would be, you know, Gmail. So it's not a specific server, it's not a specific machine. It is the whole collection of that. And then there's a job. So this is an instance of the server somewhere in space or in a data center. So now we're actually going to go into the principles of designing a large scale system. Actually, before I do that, I'm going to pop over to the Q&A. Nothing? Okay, cool. All right. So the first principle of designing a large scale system, and this is one of the first things that someone will do after they've built their, small service that's running and it's starting to get traffic, and you want to start thinking about reliability, is focus on a single server doing one thing and doing it really, really well. So let's consider a server that handles two types of requests, uploading of images and serving of thumbnails of those images or downloading of images. These two request types are pretty different. The uploading could be a lot longer and more expensive because the user has to send all of the bytes of these big things upstream in an internet connection, which might be slower than their downstream, versus serving the thumbnail images might be a lot shorter because these are tiny versions of the original one, and there might be way more of them. Because people are more likely to view a page of thumbnails than upload, a billion thumbnails or a billion images. So the initial implementation of this server might look a little bit like this, where you have one application server that handles both things. This is absolutely fine, especially early on. But as it scales, you might run into a couple problems. For example, one thing that's really important when thinking about the availability of a system or the reliability of a system is monitoring. And we want to be able to monitor the capacity, like how much can this machine or this server handle in terms of traffic, and how is it doing at any given time. And that's hard to get when you have this mix of different types of requests, because you have these really expensive uploads and you have these relatively cheap downloads. That ratio might be constantly changing over time. And in reality, the QPS measurement, or queries per second, is not going to give you a good look onto what is actually happening in that machine. So to work around that, we can create two separate servers. One that handles one type of request and one that handles the other. This makes it easier to understand the availability, the capacity, and the behavior of our system now. Additionally, not just we understand its behavior at any given moment, but we get the benefit of some isolation between these separate parts of our system. So now if there's ever a problem with the uploads, the downloads of images will still work. And remember, there are a lot more downloads than uploads. So for perhaps 90% of users, they don't even notice that there's some outage occurring. We also get some operations benefits, such as we can update the code for each one independently. And perhaps the upload gets a lot of changes, but the download stays relatively static. Now we can take the risk of every time we make a release on the upload side without affecting the download side. Sorry, one last thing about that. The downside of this, there's always a trade-off in system design. The downside of splitting up this way is complexity. Before, you had one server that did everything. Now you have two servers. They have to talk to each other. They have to be deployed in two separate ways. And you're just increasing the complexity and the maintainability, and that makes it harder to maintain the system. Okay, before I move on, just going to check. So looking at the Q&A, will these slides be available afterwards? The slides themselves, no, but the recording, yes. Is 100,000 users daily active users, monthly active users. For our services, that is daily active users because there are about 100,000 Googlers, and every Googler uses the services that I help run, just for a sense of scale. Yeah, keep putting comments in there. I'll try to periodically check it. That's a great place. Okay. So alongside keeping our servers simple, it's also really useful to keep them small. By small, I mean the number of queries per second that each server handles is small. So rather than the size of the code. And this is known as horizontal scaling. So keeping servers small sounds a little counterintuitive. I mean, we want to handle as many requests as possible, and we totally do. But if we just keep growing one server bigger and bigger and bigger, because we're just putting more and more hardware in this machine, then every time we have to upgrade it, we have to make like a hardware purchasing choice of like, do we keep buying more sticks of RAM in here? If anything breaks in that one server, our entire system is down. This is why we overwhelmingly prefer to add more and more small servers or use horizontal scaling rather than making one server bigger, which is vertical scaling. This means that if there's any problem with one machine, it's only taking down a small fraction of the overall capacity of our system. So you can imagine if a hard drive fails, then that machine is offline, but it's only serving 1/3 of our total traffic. The other two just have to handle that that fraction for the duration of the downtime. And the users might not even notice that, which is ideal because it means that we're not hurting our SLOs. Another advantage of this is that you can scale in smaller chunks. So if you just add another small machine, then that could be cheaper than buying a bigger server if you have like a smaller fleet of bigger machines. So the people who control the money will stay happy. So horizontal scaling works really well for static. Actually, before I go on, I'm just going to go check to see if there are any new questions. Yes. So is there a scenario for having a load balancer or say a cluster of load balancer? Yeah, we're going to talk about that in a little bit. There's a little section on load balancing. What tools can you use to measure what the optimal load of a server is? This is a complex question. The specific tools we use internally are not like open source, so I can't really recommend those. It's a big thing is like just measuring the data. So if you're keeping track of like how many queries per second are we serving at any given time, and like how much of our CPU and memory is a server using, then you can then map QPS to resource utilization and take a look, like as QPS goes up, resource utilization goes up. And then you know that like, okay, we're serving 1,000 QPS at 10% load, 2,000 at 20%. We want to stay under 50%. So therefore this server can handle 5,000 QPS. That's an easy napkin math. There are absolutely open source tools to do that kind of math for you. Question about Borg. I'm going to come back to that. I'll try to answer the questions that are less about the specific slides at the end in order to keep a little narrative going. And how small is small in terms of RAM CPU cores? The size, like, I couldn't give you like a good number, but as soon as things become more than, say, what you could run underneath your desk, then you probably should start thinking about horizontal scaling. Just as a really, really rough thing, but it totally depends on each, like your budget, your situation. So it's hard to give a specific number for that. Okay. Back to the presentation. Sorry, I lost the tab. Okay, so horizontal scaling works really good for static content, like images, like just JavaScript files that you need to serve, where every request is the same and therefore can be handled independently. We call those stateless requests. Horizontal scaling prevents some problems with systems that are a little more complex than just serving static files. You have a database somewhere or like a shared document stored in RAM on a machine. And when you do that, horizontal scaling becomes a little difficult because you can't just randomly assign a request to one of those small machines. Because that machine might not have the state required to respond to that request. We call that a stateful request. And as the system gets big enough to handle requests or complex enough to handle those kind of requests, then we need to start coming up with other solutions. And there are a few options of that I'll describe right now. So the first is called sharding. So the idea here is to make each server handle just a fraction of the total objects in your system. So if we think back to our photo site example, each photo that gets uploaded to the system is assigned like a unique ID in such a way that the IDs are evenly spread out over a large space. So you can think of this as like a hash map. So you're hashing the image in some way and saying, like, because of this hash, it goes to this machine. An easy way to think of it is like, it has an ID, the ID is a number, odd numbers go to server 1, even numbers go to server 2. But you want it to be spread over a large enough space so that all of your servers can get hit, hopefully evenly. We call each of those servers a shard or a slice of the data. And it's up to the load balancer to know what it means to read that ID and know what server it goes to. So the state is now stored in the ID of the request, and the load balancer understands what that means. So as your site grows, you add more servers, you increase the number of shards. You can keep going horizontally. We use this Google very, very extensively at Google because we don't want any one server having all of the data. The other idea is called caching. So here we take advantage of the fact that for many, many applications, there are more requests that just read data than write data. So we can spread those read requests over many servers, and then we just have like 1 or 2 servers that do all the writing. Because we have way fewer requests, we only need a much smaller set of servers to do that. So now this allows us to keep horizontally scaling as big as we need for the most common types of requests, which are the read ones, and then the write requests have to be handled with a little more care. So I want to illustrate what these two concepts look like. So here, this is the before state. We have a single database and a single server, and that database stores all of the entire state of our system. So as long as the system keeps growing, we just need to keep growing that database server bigger and bigger. And that means our failure domain is that server. When it goes down, our system goes down. So we can shard it. And the way that we can do this is we assign each database object a unique ID, as we were just talking about. And then the load balancer distributes those requests over the 3 shards. And within each shard, we could replicate the state for redundancy. But the important part for this concept is that, say we have 3 shards, and the load balancer, hopefully the IDs are distributed well, and the load balancer will send requests evenly across the 3 shards. So now we can scale horizontally while still having a state stored somewhere. So now just an illustrated example of what caching looks like. So this is the before state. We have a load balancer. We have 3 front ends that each have their own, sharded state. And the load balancer gets the request. It says, oh, this request, it needs to go to front end 0 because of whatever sharding principle that we've set up. Or perhaps there's an affinity that says that the load balancer knows that this client is owned by Brett, and all of Brett's requests need to go to server 0 because that is where Brett's data is. This is the opposite of load balancing, actually, because the load balancer is not balancing anything. It's just saying, send it to where the request says that it should go. Which means if that machine goes down, we have an outage for some fraction of users. We can set up a cache in order to prevent that failure domain. And in this case, we're talking about splitting up the read and the write operations. So here, instead of each front end having its own fraction of the total state, like we did in the sharding example, each front end receives a read request and goes and looks it up in a cache. And whatever is in that cache, it trusts and it sends it back. And then any write requests are always directed by the load balancer to the front end 0, which is the parent or the leader server that handles all of the write requests. Of course, now this becomes a failure domain, a single failure domain at the very beginning, like we were talking about. But these requests are much more rare. And since things are separated, if that machine goes down, we've only lost the ability to upload, and we still have the ability to download. Okay, before I go to load balancing, I'm just going to check the Q&A and see the top or htop tool in Linux has some good load data. Awesome, thank you for that. Stateless servers, like eliminating user session data. Yes, like user session data, like if you have some sort of like session variable that says like to keep, like that you need to keep persistent on the server, it's exactly what I'm talking about. Like basically anything that needs to exist outside of the request itself. Like if a server needs to know if you're logged in or not, that's a state that you can't necessarily trust the request because every request can say it's logged in. You need to verify that on your end. That's a state, you need to put that somewhere. How do you balance the engineering rule of 3 while avoiding over-engineering? I.e., did Google services always start out as a monolith, then get refactored over time, or is it architected like that from the get-go? I can't say historically, but I know that new services now are architected from the get-go to be like load balanced, horizontally scaled, things like that. And things are definitely underutilized and over-engineered a little bit at Google in the sense that like we have these really useful, powerful tools that give us the load balancing, that give us the horizontal scaling, that give us the caching that a service, when it is serving no traffic, probably doesn't need. But like those options are still there. So a service that is homed on one server is just a horizontally scaled server or service that only has one server right now and can grow horizontally when necessary. Is there an optimal object size for sharding? This is, there very well may be. I'm not an expert on that. I bet there's some really good data on that. Google has a couple of books on SRE, and there's sections on things like load balancing and the topics that I'm talking about right now. I bet there is a good answer in there. I would check that out. I'm going to come back to the Q&A in a little bit. There are still some more questions, but I want to have a balance of talking about the slides and the Q&A. Okay. Load balancing. Load balancing is so important to SRE and producing large-scale systems at Google that they are built in at many levels. They're built into the servers themselves, or like really the machines themselves, so that they can balance like individual jobs running on each of those machines. We have them at the service level. So if you're making a request to Gmail, it's distributed to all the different servers within Gmail. They are balanced even before that. And there are many layers that we have load balancing, so that way requests can be routed in real time while being aware of like the global traffic state, the global utilization state of our system. So here's a typical load balancing setup where you have one machine that routes requests to a series of backends. Or in this case, we have since there can be load balancing at multiple layers, a single server might not have access to, or might not be able to handle the entire request. It may need to make calls to other backends. And this is called fan out, where a single request will go to a machine or go to a server, and then that server, as part of its business logic, needs to make requests to other servers, and that gets load balanced, and so on and so forth. And this is great because we break out the load across several backends rather than putting all of the load on one root machine, that server at the very top. Now we have all these little things that are just really good at what they do. Backend 0, it's really good at user authentication or something like that. So that's all it does. And then server can focus on what it does best. Great, we've applied our principles. However, one of the downsides is fan in. So this is, the server has sent requests to all these different backends, and all of those backends need to respond. So now the server has to handle all of the responses that are coming back in, possibly from many, many different servers. And at the same time, keep handling further requests. So now this one root server can be the bottleneck of our network. And that can lead to dropped packets. It can lead to poor latency for our users as the CPU or memory or whatever get loaded up responding to all of these, or dealing with all of these responses. So a way that we can handle this is having a tree system. So rather than having one root that sends requests to everything, we break it up so that way there's a tree. So one root will make a request to some other machine or some other server, then it makes a request to a couple of other servers, and so on and so forth. And now we still have this distributed handling, so we have the benefits of having servers that are really good at one thing. The load is distributed, but we are lowering the risk of fan in, because at any given node in this tree, there's only a few other nodes that could possibly make responses to it, which could overwhelm it. The downside of this, because there's always downsides, is that we have to be aware of cycles. When you make trees, it's really easy to actually turn it into a graph. So instead of leaf 1 handling everything and not making any requests, perhaps leaf 1 is making a request to leaf 0 over there in order to get some piece of information. And now we have a cycle. And when you have a cycle, that can result in a recursive loop that doesn't end, and it can lock up your machines. So talked a bit about how we handle distributing requests for load. A very tricky thing is how we manage the consistency of data, because we can't just always have one server that is the right. We can't just always have one database that everything looks up. We need to have things distributed a bit. And this brings us to the CAP theorem. So consistency, or actually before I go to that, I want to check the Q&A once more. Is the load balancer much more reliable than shards? The load balancer is typically a thing that is utilized when you have a sharded system. So the load balancer is the thing that knows which shard to request. So a request comes in that says, I want image ID 1. The load balancer says, oh, image ID 1, that's an odd number. I'm going to send you to server 1. And so on and so forth. So the load balancer is a key part of the sharding. How do you store configuration in a distributed system? If it's multi-tenanted application, what is the ideal approach for storing and retrieving config? Ideal approach, I never want to say that there's an ideal approach because everything always has a trade-off. And so it really depends on the system. But a way that you can do it is, I guess first I want to say, I'm talking about configuration for the service itself. So this would be something like, what if you have like an experiment running and you say, I want this button to be red because we've determined that red is the best color. And that is defined in a config somewhere. That could roll out with your binary. So when you push the code, or the actual binary that runs the server, you can also push the configuration that defines how that works. Or maybe not at the same frequency, you could push it more often, but in the same way. So it goes to, I can talk so much about this. I really don't want to right now because this is something that I deeply work on right now. So I'm actually going to hold off on that question, and maybe at the end we can get to it. What is the most frequent used sharding principle for uniform distribution? I can't say most frequent. I would look up some. I'm sure there are some really common ones. I think it really depends on how you structure your IDs, and it might depend on what kind of data you're referring to, where your different like sharding or hashing algorithm might be better than another one. I would say that there's the risk of over optimizing. Like if you can just come up with a simple one that, maybe it's not perfectly distributing your shards by traffic, that's fine. Just having something is more important, and then you can tune it once the shards are up. Techniques for cache invalidation. There's a lot to say about this. I don't want to go into that. I would say check out the SRE book. Okay. I'm going to pause there, and I will come back to questions in a couple more slides. So back to the CAP theorem. So consistency and availability are both admirable goals, but they can seem mutually exclusive sometimes. And the CAP theorem describes that balance. So you can imagine that if you have two systems, like you have shards or something, and something causes the network between them to break. And now some section of your system and another section can't communicate with each other. That means that these systems can't be consistent with each other because they don't know what the other one is doing. The CAP theorem says that you need to pick two of either they're consistent, they're available, or they can tolerate the partition event. So when a partitioning occurs, the system must make a decision. So we have these shards, something means they cannot communicate with each other. It can continue to accept writes, knowing that the nodes in one of these islands may issue reads to see old data from the other one, which means it's trying to access things that don't exist, and now there's an inconsistency. Or it can see that there's a partition and say you can only read. So that means we are staying consistent, but we're no longer available because we've lost a fraction of our functionality. And that is the CAP theorem in principle. You're deciding what's more important. The system is always consistent, or the system is always available. Always is in quotes because nothing is always available. At Google, we have some systems that favor consistency and some that favor availability. When possible, we try to focus on availability because that's what we care about for our users. And that means we have to design systems that are okay with being consistent eventually. Meaning if something gets out of sync, that's totally fine. It'll eventually catch up. How do we deal with this then? We can use this concept of distributed consensus. So a distributed consensus algorithm is one where, or an approach for distributed consensus is to preserve that sort of consistency when things are so disparate and spread apart. A way that we can do this is by having leader election. And what this means is that we have n servers, and one of them takes on the special role of being a leader. And I think the next slide goes into more detail, so I'm going to hold off on talking about that. I'm actually going to go talk about that. I think that's more interesting. I'm going to skip ahead a little bit. Yeah. Oh no, sorry guys. I thought there was more details on how these principles worked, but I might have missed that in the slides. So in that case, I can only really give a surface level description of what these things are. So a couple of ways that we deal with eventual or distributed consistency. First, we have leader election. So this is, thinking about that caching system where we have one leader that its job is to define what writes are possible into our shared readable space. I'm going to skip ahead to the distributed locking. So in this idea, we have this shared state, and any machine can say, I'm going to make a change to that. And it will grab a lock saying, I am the one that is making a change. And as long as there is a lock, nothing else can make a change to that. We can use like namespaces to basically, implement some sort of sharding system where we're distributing what data and what state is owned by a set of our machines. And I'm going to skip the next one too, because I'm not exactly sure what it's referring to, and talk about message queuing. So here is one where basically a server can say, I am making a change, or here is a change in state, and put that onto a queue. And then at whatever frequency the consumer of that data needs to retrieve it, it can pull things off of that queue. So that queue will just constantly have these different changes to the state, and the consumers of that queue will say, I'm ready to make a change, and it'll grab one of those and make the change. It will grab the next one and make the change. And until that queue is empty, the other systems will keep making the changes to get up to speed. There's always a cost to everything, which is a big principle of this. And distributed consensus is no exception. It's really expensive. The most efficient implementations still require like a round trip request between, you have your leader that says all writes need to go through me, and the other machines or the other servers that make requests to that. You need a lot of replicas, because in order to be resilient, we have to have replicas of all of these things. And as a result, at Google, we really try to use a lot of these things sparingly because they're super expensive. But they do underlie a lot of our most well-known services. Last thing, I want to talk about how to iterate on a design once you have one. First thing is to look for the bottlenecks. So Bottlenecks or like a single point of failure, these represent, compromises. There's always trade-offs. A bottleneck is not a failure in a design. At some point, you're going to have to make a compromise. And that said, a bottleneck can be the thing that prevents a system from scaling up. And through iterating on your design, you can identify those things and apply these principles once more to come up with a way to eliminate that bottleneck. A way that you can do that is create a box diagram showing the processes. We did a bunch of those earlier in this presentation. See, where does data go in this flow? Is there a single spot where all the requests have to go through? What would happen if your load changes 10x? Can that one server handle that much change? What if the type of traffic changes? So instead of storing JPEGs, you need to store movie length videos. Same servers, same amount of traffic, but it's a different shape. And now you need to handle that. Next thing, so talked about looking at single points of failure or the bottlenecks. Next thing is looking at things in terms of resources. So we've built out this system. We don't know how it's going to behave until we start seeing traffic hit it. So if the traffic comes in and we're seeing that shard 1 is getting 90% load and shard 2 and shard 3 is at 10%, well, your sharding algorithm has some problems with it. And you need to figure out a way to rebalance. And that's something you don't even know. You will not know until you monitor your system and see it in action. How can your design accommodate change? So in this case, this is why we advocate for small, simple servers. If you need to make a change, it's a lot easier to add a second small server than to replicate your giant monolith. What if you need to distribute it across continents? So you're getting a bunch of users in Europe. You don't want them to make a round trip to your data center in North America. You need a way to deal with eventual consistency now, because it's going to be a lot harder to keep the European state in sync with the American state. And what happens when everything's running really smoothly? Maybe it's time to start thinking about simplifying things. If everything's going great, perhaps you are spending a lot of money on really fancy load balancers and 1,000 replicas of your servers. Perhaps it's time to simplify, turn some stuff down. That is a big part of what it means to be an SRE, is to think about cutting stuff in addition to adding things. So in summary, talked about a bunch of different things, some architectural principles of how you can compose a bunch of small pieces to build this large complex server or service that can be resilient to a lot of different changes. We talked about handling failure. So, if something wrong happens, machine fails, then how does your system heal from that? So using load balancing, replicating, sharding, things like that. And we talked a little bit about how to manage consistent state that is distributed over a variety of servers. For further reading, Google has a collection of books on SRE. They are free. I highly recommend checking them out. They tell a story of Google's history in the space, as well as a lot of the lessons that we've learned through many, many failures and successes too. So thank you very much. I'm going to take a look at the Q&A with any remaining time. I hope you learned something from that talk. Okay, I'm going to go to the Q&A. I'm actually going to pick up from the top. Is gRPC used in SRE? You bet. RPCs are the fundamental way that every single thing communicates at Google. So yes, very extensively. Can the load balancing server convert a request from a client to a peer-to-peer session? Good question. Probably, but I don't have enough experience on that to be able to say too much on it. Does Google prefer row or column-based sharding, or does it vary based on data in the service? An easy answer is for me to say it varies because I don't know the answer. And for most of the time, the answer is always, it really depends on the system. I wish I could answer that a little bit better. How do we deal with network latency that might occur due to the tree structure? Great question. This is absolutely one of the trade-offs of a tree structure. To illustrate this, I'm actually going to go back to that slide. Let's see if I can find it. Here we are. So you can imagine that, let's say it's 100 milliseconds to respond to any of these requests. In this case, the server makes a request to each of the backends. They each take 100 milliseconds, but because that's happening in parallel, now the overall latency is 100 milliseconds because it's all happening in parallel. Here, now it's 200 because it's 100 to go from the root to node 0, then another 100 to go from node 0 to leaf 0. This ends up just being a trade-off that you have to make. Like, you have to be aware of how many nodes a given server needs to go communicate with, and is it acceptable to have these serial requests and still meet your SLOs? So everything is going to come back down to the SLO, and an SLO might say something like, we need to respond to every request or 99% of requests within 1 second. So that means you have a budget of 1 whole second to make all these requests. And you can keep adding layers until you hit that budget. And once you've hit it, then you know, I can't do any more layers. We have to start doing it horizontally instead. Does Google have their own custom caching solution? Do you also utilize Redis? Yeah, I want to say yes, but it's not something I know too much about. Google is very big, and the services that I've interacted with are probably a very small part of it. Load balancer looks like a binary search tree. Same logic applicable? Absolutely. A lot of this stuff is the same fundamentals of computer science, data structures, algorithms. And that's reflected in the kind of system design interview questions. Is it's always going to come back to those principles. If most of the systems are eventually consistent, does that cause any consistency issues? If yes, how are they resolved? So this is something where I wish I'd gone a little bit more into the details of, but that's the fundamental problem of eventual consistency. If you have a system that is eventually consistent, what you're effectively saying is, I'm okay with some parts of the system being inconsistent at times, because it's okay that after 15 minutes, they're eventually all in sync again. And that's totally fine for things like, if my profile picture on LinkedIn, to me, looks good, but to someone in Germany is still my old one for 15 minutes, that really doesn't matter. For things like, I've changed my password because I thought my account was compromised, you can't be as eventually consistent. That latency between when every system or every server in your system has the same state has to be a lot shorter. And so you have less tolerance. It really depends on what the system is trying to do. How they're resolved, I'd take a look at things like the master election principles. Do you use Raft, Paxos, or a proprietary consensus algorithm? Great question. Unfortunately, don't have the answer to that. If a leader goes down, do the replicas get elected as leader? Yes. Again, leader election is not something that I am super familiar with, because it's not something that we do in our systems. And I believe that the answer is that all the different servers in the collection are trying to become leader. And if there is no leader, then there will be another election to appoint what that leader is in its absence. How often do SRE and software engineering roles overlap? I would say very. My title is software engineer, and my role is site reliability engineer. And what that means is that SREs have to have some sort of software engineering skills, in addition to like ops side of skills, in order to do the job of maintaining a big distributed system. We just like can't scale well where we have to click the buttons manually to deploy, you know, thousands of servers across many continents. We need to build software to do that for us. And that means that SREs who do the maintenance, the operations, have to be software engineers in order to automate all that stuff away. So they overlap a lot. That said, SRE does have a big operations component, which, you know, I'm on call. If something breaks, I have to go respond to that. There's no software engineering skills in there. It seems like distributed system is similar to Kafka. Does being familiar with one help inform the other? I imagine the answer is yes, but I'm not too familiar with Kafka, so I cannot say specifically. Can you talk about your time at Codesmith? Any recommendations for Codesmith students and grads? Yeah, I'll talk a little bit about it. I had a great time at Codesmith. My production project was a system where you could like click on any sort of structured data on a website like Reddit, and it would like scrape that and then put that into a backend that would then serve a copy of that data effectively. So that way you could turn any website that had like a structured UI into an API. Is really cool. I focused on the backend because that just vibed with me best. After graduating, I took a backend like Node developer role at a healthcare startup in LA and worked there for about 2 years, and it's really cool. Then went to Google and did like the software engineer interview. Didn't know what SRE was, and during the team matching phase, I got paired up with I met my manager who pitched me on SRE. I thought it made so much sense because it's a big focus on doing things the right way, do it slowly, fix things, which worked really well with me. So I ended up doing that and have been enjoying that since. Recommendations? You know, a thing that Codesmith says all the time is like to just apply to things. When I was a student at Codesmith, I like was afraid to apply to Google and, you know, similar giant tech companies. And I wish I hadn't been afraid. It really took applying to those kind of companies a year or 2 years later and like completely bombing it. And then like after the interview being like, that wasn't so bad. They gave me the confidence to keep it going. And, you know, it ended up resulting in me working at Google 2 years later. A bump on the board question. Is the service you work on built on Borg? Yes. So a super brief overview of what is Borg. If you're familiar with Kubernetes, Kubernetes is the open source version of Borg. And Borg is basically just our cluster management system at Google. And almost everything that we do is built on Borg. So that means that we get a lot of these like replication things for free because Borg handles all that for us. Definitely recommend looking into Kubernetes. It's big, it's complicated, it's built like the space shuttle. It's super cool, but I wouldn't recommend looking at that until you already have a really big server or a service that would benefit from large scale cluster management. What was I'm going to just answer these last two questions, I think. What was your software background before Codesmith? I studied material science and engineering before going to Codesmith. I took a total of 1 CS class, but had like that like engineering kind of mindset from college. After I did like a bunch of like for fun, like personal projects in like Python, but like didn't really do much more. I was trying to find like software engineering roles because in materials, the kind of roles that I wanted weren't exactly what I was most interested in. So I was looking for software roles, and wasn't really getting what I wanted out of those interviews and applications. So I went to Codesmith to turn that like sort of self-taught personal project kind of skills into something more concrete. And it ended up working out. It gave me exactly what I needed there. Does my job involve international travel? Yes, in the sense that in SRE, half of our team is in a time zone that is on the other side of the world. And that means that in LA, we cover on call 9 to 9 a.m. to 9 p.m. Pacific time. And then we have the team in Dublin, which handles 5 a.m. to 5 p.m. Dublin time. And we are all on the same team, same titles, same projects, same servers. And that means that we need to talk to each other. And I joined not too long before COVID occurred. So that means I didn't get the opportunity to go to Dublin, but I'm hoping that that can happen very soon. All right, I think with that, I'm going to wrap up the Q&A. Thank you all for the wonderful questions. Those were super interesting, and definitely challenged my own knowledge of distributed systems. So I appreciate that. It inspires me to go look for more things as well.